All right, so we continue with the second talk by Eugenio Calabi from UPA, about the percentage of birational geometers if increased a little bit in general. So, Eugenio,
Thank you very much, Eugenio. So thank you for coming back. And today we are going to continue discussing the Calabi problem that I explained yesterday. So let me just remind you that the problem asks which complex varieties admit Kähler-Einstein metric. And so today I will review the Calabi problem from last time. Then we will go a little bit deeper into the birational geometrical aspects. And then we come back to the Calabi problem for final threefolds, and I'll explain how we use these tools from birational geometry to make progress in this problem. So let me start by just reviewing what I explained at the end of my lecture yesterday. So we want to understand which compact complex variety that meet the Kähler-Einstein metric, and let me to start with the setup. So we are given a complex compact variety of dimension m. So this means that it's given by charts, and the way that we are going to record this the complex structure is by this has been discussed a lot this week. This almost complex structure on the tangent space. And now let me remind you first of the definition of a Kähler metric. So this is just a Riemannian metric that is compatible with the complex structure of X. So this means that the G is compatible with J in this way. So this respects J and then also commutes with the parallel transport. And just a note, as Nancy explained in the first day of the conference, not every complex variety meets a Kähler metric, but when it doesn't meet, we say that it is a Kähler variety. So now let me just start with some examples, remind some examples of the complex projective space. It meets the well-known Houdini metric, and if you restrict it to any variety, you get that projective varieties are also Kähler. But as we saw today, this morning, for a Kähler variety, there is an infinite dimensional space of possible Kähler metrics on X. And then the motivating question is, are there some canonical Kähler metrics on X? And today we're going to be discussing one such, one possible notion of a canonical Kähler metric. Which is so for that, let me just change the notation a little bit. Instead of working with a metric, Riemannian metric G, when we are working with the Kähler variety, it's more suitable to work with the true form. So you can cook up a true form from a Riemannian metric on the complex variety in this way, and from this we can also go back from the true form. We can recover the Riemannian metric, and the Kähler condition from the point of view of the true form is just asking that the true form is closed. And so now, and in this case, we call it the Kähler true form. And associated with we can look at the cohomology class. And now I think this was introduced by Rudy also this morning. We can consider the space of all Kähler metrics in the same given cohomology class, or in other words, this was the way it was introduced this morning. This is called the space of Kähler potential. So it's parametrizing all the Kähler metrics with the same given cohomology class. And also, if you take a Kähler form, you can associate another closed true form, which is the Ricci curvature true form. And so this can define a cohomology class. And it turns out that this is a remarkable fact that this curvature true form does not depend on on the original Kähler metric. So this is just obfuscating the first Chern class of X. So this is independent of the Kähler form. And now the Kähler, let me just remind you, the Kähler-Einstein, what is the Kähler-Einstein metric? So this is a Kähler metric for which the Ricci 2 form is just a constant multiple of the given Kähler metric omega. And so by rescaling, we can assume that this factor is either -1 or 0 or 1. And this was the problem that was posed by Calabi and advertised in his ICM 1954 lecture. So which compact Kähler varieties need a Kähler-Einstein metric? And if this metric exists, then it is unique. So it is canonical in this sense. And then from the point of view of the space of Kähler potential, the way that we look at Kähler metrics, that they are minimizers for a certain functional. So this is what is called the Noguchi functional on this space of Kähler potential. So a Kähler-Einstein metric is a minimizer for this Noguchi functional. And so we have already seen that for Riemann surfaces, from the Poincaré uniformization theorem, we see that every Riemann surface admits a unique Kähler-Einstein metric, and the sign of the curvature just depends on the G. So this is what we saw last time, and in general, we have so this is we're given a Kähler variety, and we want to understand when it has a Kähler form, and so I just recall that the canonical class is recording the Ricci curvature is associated to this metric. And so a necessary condition for the existence of a Kähler-Einstein metric is that the sign of the canonical class is well defined. So it's either negative or the uncanonical class, either negative, 0, or positive. And in algebra geometric terms, we say that either the canonical class is ample, or it is numerically trivial, or it's anti-ample. And so this corresponds to these 3 big classes of varieties: canonically polarized varieties, Calabi-algebraic varieties, and Fano varieties. And finally, I remind you that for the first 2 classes, the problem has been solved. So Yau first proved in 1976 that for varieties with numerically trivial canonical class, you always get a Kähler-Einstein metric, and shortly after that, Aubin and Yau proved independently that if the canonical class is ample, then at X also admits the Kähler-Einstein metric. However, for Fano varieties, X, the Fano variety may or may not admit the Kähler-Einstein metric, and determining which Fano varieties admit the Kähler-Einstein metric is the problem that we are interested in. So, okay, so let's see which Fano varieties admit the Kähler-Einstein metric. So some examples of the projective space that the Fubini-Studio metric is in fact a Kähler-Einstein metric, and also more generally any rational homogeneous space admits a Kähler-Einstein metric. Now, on the negative side, so this was already known to Matsushima, and it was also discussed this morning, that if a Fano variety admits a Kähler-Einstein metric, then necessarily its automorphism group must be reductive. So this allows us to construct the first non-examples, and so these are Fanos with no Kähler-Einstein metric. So this is, for instance, as I mentioned yesterday, you can take as examples the blow up of P2 in 1 or 2 points. So I wrote here what are the automorphism groups of these varieties, and then you see that they have this GA factor here, and so they're non-reductive, and so this surfaces do not admit Kähler-Einstein metrics. And so let me take this opportunity to remind you of the classification of the Lopez surfaces. So this was already known to the Italian school, that there are, as I said, 10 deformation families of Del Peso surfaces. Del Peso surfaces are just Fano surfaces. So they can be CP2, CP1 cross CP1, and then CP2 blown up in at most 8 points. And from this list here, there are exactly 2 with non-reductive automorphism group. And so these are the ones that do not admit Kähler-Einstein metric. And it was proved by in a series of works by Tian and Yau that except for these 2 examples, all other Del Peso surfaces admit Kähler-Einstein metric. And here I should say that this was really a case-by-case analysis, and it amounted to actually showing that the Lagrangian functional had a minimum, and for that we have to solve the Monter-Ampere type equations, and now, as I said yesterday, at that time it did not seem it was approachable, the problem of classifying 3-dimensional Kähler-Einstein on threefolds. Okay, so then I want to now introduce the notion of case stability. So this will be, in the end, this will be an algebraic condition that captures the existence of Kähler-Einstein metric. So you start with the Fano variety, and so the first thing that I want to explain is what a test configuration is. So a test configuration for X is just a family. It could be a degeneration of my given Fano variety. So it is a family of projective varieties parameterized by the affine line, with the property that, so for every t different than 0, the variety xt is isomorphic in my given variety X. And then over the origin, I have some degeneration. So I drew something nice here, something irreducible, but it could be reducible. So it could be pretty badly singular. So if you take any degeneration of my original variety, so the outside the origin, all the fibers are isomorphic to X, and then at the origin, over the origin, anything can happen. So a test configuration is a little bit more than just a degeneration. We also have a C-star action. Well, so you have the usual C-star action on A1, and we have a C-star action also on family X, such that this morphism is equivariant. So we have this equivariant family, and also we have some relatively ample line bundle in this family that we are going to use to embed it in some big projective space. So associated to this test configuration, we can define what is called the Donaldson-Futaki invariant. So I will not write down the formula for this, but I will explain what this Donaldson-Futaki invariant is. But it was originally defined by Tian in terms of weights of the action. So you look at the action, you have a limit action on the central fiber, and then from this we can hook up from the weight of the action we can hook up this invariant, and later on it was reinterpreted by Donaldson as some product of cohomology classes on X. So here on X you have the relative canonical class, you have your given line bundle L, and then from those you hook up this invariant. But instead of giving you a precise formula, let me tell you what this invariant is measuring. So if you start with a test configuration like this, what you can do, so you can use, as I said, there is a line bundle involved in this picture, and you can use this line bundle to embed this family in some big projective space. And so in this big projective space, you have this degeneration of your given Fano variety, and then you can pull back your the Fubini study metric from the projective space. You can pull back to the members of this family, and in this way, what you get is in the space of Kähler potentials, we have this algebraic array corresponding to this X configuration. And as I said, the existence of the Kähler-Einstein metric is equivalent to having a minimum for the Mabuchi functional. So what this Donaldson-Complat invariant is nothing but the limit of the derivative of the Mabuchi functional on this algebraic array defined by this pattern. And so this is what it really means. And then once you have this Donaldson-Complat invariant for any given test configuration, we can define the notion of K-stability. So we say that the X is K-stable if for every non-trivial test configuration of X, the Donaldson-Complat invariant is positive. We say that it is K semi-stable if for every non-trivial test configuration the Donaldson-Complat invariant is non-negative, and somewhere in between you have this notion of K polystability. So X is K polystable if for every non-trivial test configuration the Donaldson-Complat invariant is non-negative, and it is 0 if and only if the central fiber is isomorphic. And so we have some trivial implications. So K stable implies K polystable, and implies K semi-stable. And this and it turns out that if you think about this interpretation that I gave you for the Donaldson-Complat invariant, so if your variety has a Kähler-Einstein metric, then the Mabuchi functional will have a minimum, and in particular, if you take any algebraic array with the limit of the derivative of the Mabuchi functional, it must satisfy this condition. So we see that if X admits Kähler-Einstein metric, then it is K stable. And it was conjectured by Yau, and Donaldson that this would actually be an algebraic characterization of existence of Kähler-Einstein metric. And so this is what they conjectured, and it was and now, as I said, this is a theorem. So we know that X now is admits a Kähler-Einstein metric if and only if it is K polystable. And okay, so let's try to understand this notion of K polystability, and for exploring this notion, I want to take a step back and discuss birational some aspects of birational geometry. So to introduce what is the main goal and the main point of view of birational geometry, let me start by discussing the classification problem in algebraic geometry. So in dimension 1, we can easily classify projective curves. So as I explained yesterday, so here you have first of all, we have this discrete invariant, the genus, and then that will roughly divide the Riemann surfaces into various classes. And now, after you decide which class your Riemann surface is, you want to now classify what are the Riemann surfaces with a fixed genus. And then this was already known to Riemann. There is a moduli space parametrizing all smooth projective curves of genus G. So this is so in a sense this is the classification program for Riemann surfaces. Plus, you find the genus, and then once you know the genus, you have this moduli spaces for each fixed genus. Now, if you try to run the same program in higher dimensions, then it turns out that you cannot do that because there are way too many isomorphism classes. And so to make this precise, let me remind you the notion of a blow up of, say, projective plane. So if you have a projective plane, you can hit any point of the plane and blow it up. So by that, I mean that I want to remove the point and replace it by a P1 that is parameterizing all the tangent directions of this point. So more formally, what I can do is that I can project take a linear projection from CP2 to CP1. So this is given by this formula, and take the closure of this graph. So this is only not defined at the point from which you project. And then if you take the closure of the graph, this is precisely the blow up of P2 at the point. And so this is the picture. So you see that if you remove the point, then over the punctured plane, this map is an isomorphism, and then you replace your point by what we call an exceptional divisor CP1 over it. And so I could start with the plane and start blowing up many points, and then one after the other in a sequence, an infinite sequence of points, and then this will lead to a huge amount of different non-isomorphic surfaces, and so this is why I cannot hope to have a nice picture that I had for Riemann surfaces. There are way too many isomorphism classes, and so instead, what we will do, instead of classifying up to isomorphism, we will classify up to some weaker equivalence. And this is, so let me remind the definition of a birational equivalence. So we say that two projective varieties are birationally equivalent when they have isomorphic dense open subsets. And this is, for instance, like a P2 and a P2 blown up at a point. These are birationally isomorphic surfaces. So algebraically, this condition is equivalent to saying that the field of meromorphic functions on X and on Y are isomorphic. So this is the algebraic interpretation of this birational equivalence notion. And now this is the notion that we want to use to try to classify projective varieties. So now this is how the classification problem in algebraic geometry goes in higher dimensions. So the first step is that can be summarized in this way. Given a projective variety, we want to find a simplest representative of X in its birational class. So this is what we call a minimal model of X. For instance, if you sort of easy to argue that if you have a surface, you have P2 and then you have P2 blown up at a point, P2 is simpler than its blow up. So in the sense we want to do this in general, get a simplest representative in the same birational class. And then once we have this, then we hope to be able to construct and describe the modelized spaces of minimal models with some fixed invariants. And so this is a summary of how the classification problem in algebraic geometry. And today, even though I have to say that the case stability is also related to the step 2, but today we are going to be more concerned with the first step, find the simplest representative in the birational class. And so this is what is called the minimal model program. And so the goal of the minimal model program is that given a projective variety X, we want to find a simplest representative in its birational class. So the minimal model of X. So in dimension 1, there is really not much to be done, because for curves, for smooth curves, isomorphism is the same thing as birational equivalent, and so this was pretty much achieved by Riemann in the 19th century.
Carolina,
yes.
Just to be sure, why taking blow-ups doesn't change the fields?
So in general, if you have two, so the field is the field of meromorphic function. So if they have a common open subset, you can always restrict to this open subset, and so the functions are the same. So basically, if you have a dense open subset of your variety, this will have the same function field of your original variety. So restricting to open subsets in this heuristic topology, they're huge, and so so you don't lose any functions by restricting to open subset. So if they have dense, isomorphic dense open subset, they have the same function. Okay, so this is for curves. There's really, I mean, nothing. Also, if you try to blow up a smooth curve, actually you don't do anything, because when you blow up, you replace the point by all the tangent directions at this point. But if you're on a curve, there's only one tangent direction, and so it's really the blow up is an isomorphism. So you don't do, you cannot have anything different. Now, in dimension 2, we have seen that you can actually blow up surfaces, and in this way you get new surfaces. And so here, really, we do have many non-isomorphic birational equivalent surfaces in the same class. And but the first step of the classification problem can be carried out, and this was developed by the Italian school and was finished by the early 20th century, and it turns out that for surfaces, blow-ups are the only operations that one needs. So what was known already to the Italians is that if you start with any smooth projected surface, complex surface, you can do blow downs, and by doing after a finite sequence of blow downs, you get to a minimal model. So this is a surface that does not admit any non-trivial blow down. And so this is the minimal model program for surfaces is just taking a sequence of blow-ups or blow downs. Now, in dimension 3, you'll see the situation is much more complicated, and a lot of people, of course, worked on this, but the program was finally completed by Mori in 1988, and actually that would have been the Fields Medal in 1990. And then more recently, in dimension at least 4, a big chunk of the program has been proved by Bicart, Piccini, Haken, McKern. So the full minimal model program is not known in dimension greater or equal to 4, but we know enough to produce minimal models in most important situations. And as a consequence of the minimal model program, we know that every projected variety can be constructed from these 3 classes: canonically polarized variety, so positive ample canonical class, Calabi type varieties, which is the canonical class numerically trivial, and the Fano varieties, the canonical projected varieties with anti-ample or with ample anti-canonical class. And I wanted just to make a remark that for Calabi type varieties, so those with numerically trivial canonical class, there is a structure theorem, which is known as the Bogomolov decomposition theorem. It says that after finite État cover, this variety may be written as a product of 2 types of varieties: abelian varieties, hyperscalar, and a strictly Calabi variety. So this is a very important theorem, and the reason why I mentioned it is that if you go to if you want to learn the proof of the Bogomolov theorem, it starts exactly by taking Kähler-Einstein metric on X. So you know that it admits a Kähler-Einstein metric, and then you start working with this metric. So this is to show that the existence of Kähler-Einstein metric, even though it is a sort of an analytic problem, it has also a strong impact in algebraic geometry as well. Okay, so now let me discuss the higher dimensional minimal model program. So as I said, for surfaces, this was known a long time ago, and the minimal model program consists of sequences of blow-ups. And in higher dimension, the situation is much more complicated, and I would like to discuss 2 difficulties that arise in higher dimension. So the first of all is that there are some new birational maps that appear in the minimal model program. So you don't have only blow-ups, you also have this maps, that these are called flips and flops. So these are sort of surgeries in your spaces. For instance, you can have a 3-dimensional space, and then you can remove you remove a curve and then you replace it by some curve that is glued in a different way. So this is what we call flips and flops. And so these are much more difficult to control than blowups. So this is one first difficulty that appears. And another one is that singularities are unavoidable. So even if you are only interested in finding minimal model for smooth varieties, there is no way that you can achieve this in the realm of smooth varieties. So you have to allow for singular varieties. And actually, this was a difficult, so this was understood very early. But the difficult thing here is that you need to allow singularity, but you cannot allow any singularity because if you do that, you don't have theorems. So your theorems usually will have to have interesting and meaningful theorems. You will have to impose restriction on the singularities. And so here there is a very balanced situation that you have to find. What is the class of singularities that are mild enough so that your theorems are still valid and they are flexible enough to let the minimal model program run? And this led to some new notions of singularities. So these are called singularities of the minimal model program. So there is a bunch of different notions: terminal, canonical, kilometer terminal, which usually called KLT, well, canonical, and so on. And so this took some decades for people to come up with the right definition. So I would like to give you the definition of one of this type of varieties. And for that, let me introduce what we call the log discrepancy. So if you start, you will start with some variety X. And now consider any birational morphism from another variety Y to X. So you can think of this F as, for instance, a blow-up. And then take any prime divisor on Y. So for instance, you should think of this E as the exceptional divisor of a blow-up. And now, because this is a birational morphism, so it will restrict to an isomorphism on some dense open subset. The canonical class of X and Y on this open subsets, they are the same. And so they will be different exactly on the divisors where I don't have an isomorphism. And so I can compare the canonical class of Y with the pullback of the canonical class of X. So they will be the canonical class will be equal to the pullback plus some contribution of the exceptional divisors. And then if I take the coefficient of this exceptional divisor, this is what we call the log discrepancy. Well, for some technical reason here, I'm going to add 1 to it. But you should think of this discrepancy. So this is measuring the coefficient of this divisor in the relative canonical. So this is where the canonical class differ. And now I can define Kilometer terminal singularities. So we say that X has KLT singularities for every birational morphism and for every prime divisor E on the domain of this birational morphism, the log discrepancy is greater or equal to 0. So if you've never seen this notion, I do not expect that you will be able to appreciate. So as I said, it took decades for people to realize that this is the good definition. But now we know that this is the nice definition. And now let me define this important notion of a few fun varieties. So this is basically the fun varieties with singularities mild enough. So this is a projective variety, ample anticanonical class, and at worst KLT singularities. And so, for instance, this is this class of varieties is the Q-fun varieties. They're very much studied by Beerkart and geology again, the field's modeling in 2018. And now, why is this connected to the existence of Kähler-Einstein metric? And so this was proved by Li and Xu in 2014. So, and I think this is the first time that this notion from the minimal model program appear in the constant in the context of Kähler-Einstein metric. So they showed that when testing K-poly stability, which is the equivalent to Kähler-Einstein, it is enough to consider spatial test configurations. So spatial test configurations are those for which the spatial fibers are Q-foundable variables. So as I said, when we define test configurations, the spatial fiber could have many reducible components that could have very bad singularities. However, for the purpose of checking Kähler-Einstein metrics or K-poly stability, it is enough to consider the generations that are mild, so for which the central fiber is a Q-fiber. And now I will explain. So this is actually probably the first time when people realize that these tools, these techniques from the minimal model program could be applied to K-poly stability. And then since then, this has been very much investigated. And nowadays, there are some what we call evaluative criteria for K-poly stability. So let me explain one of these criteria. So if I remind you, this is just if you have any birational morphism in a prime divisor of Y, there's an exceptional divisor of Lola. We have already, I have already defined the law of discrepancy. And let me say why I call this evaluative criteria or this evaluative notion. So if you have any birational morphism from Y to X and a prime divisor on E on Y, this defines a valuation in the function field of X in the following sense. If we have a neuromorphic function on X, because it is birational to Y, this can be seen as a neuromorphic function on Y, and then you can check what is the order of zero or pole of this function on E. And so this is a valuation in the function field of Y. And this notion of law of discrepancy, in fact, does not depend on the divisor. So if you take any other model Y with a divisor that defines the same valuation and you compute the law of discrepancy, it will be the same. So it does not really depend on the divisors, but only on the valuation that is associated with it. And we can define other invariants to this valuation. So one that is going to be very important to us is what we call the expected vanishing order. And this is defined in this way. So the expected vanishing order of E. So we have to compute this in this integral. So here we take this divisor, the pullback of the uncanonical class, and we subtract some multiple of the divisor E. And so we take the volume of this divisor. So this volume is something that matches the rate of growth of sections when I take multiples of this divisor, this line bundle. And so I compute this volume, and then I integrate it from 0 to infinity and then normalize it. And so this is the expected vanishing order. And let me say make a few comments about this notion. So first of all, even though I define this as an infinite integral, it turns out that this integral can be computed. This can be computed in finite level. So I define this what we call pseudo-effective threshold. So I start with, so remember, take that X is funnel. So the pullback, so the uncanonical is ample. So if I take the pullback, this is something. This is going to be a semi-ample line bundle on Y. And if I start subtract a little bit of E, this is still going to be have sections. And so the volume is going to be non-zero. So at a certain point, this is exactly when I reach tau, now this line bundle that appears to the right is no longer is is no longer effective. And so up to this point, that the volume is non-zero, and then it becomes zero. So if you want to compute this integral, you know, you just have to do it for this until this value tau of e. And I should say also that if you know enough the geometry of your variety, you can actually compute this integral. So this is not something abstract, because for instance, if you start with an ample line bundle, then the volume is just the top self-intersection. So for instance, if I define this is another threshold, this is the mid threshold. So this is the maximum x that I can subtract from the pullback at the end of the canonical so that it is mid. So if my divisor is mid, so if our x is less or equal than the sigma, then the volume is just the top self-intersection, the top self-intersection of the divisor. And so this is something very easy to compute. If you know your variety, you compute the top self-intersection, and then you just integrate it. So this is going to be a polynomial function on x. Now, after if you take the values of x that are, say, between sigma and tau, what is going to happen is that this exceptional divisor E is going to appear in the stable base locus of your line bundle. And so to compute the volume, you have to take the top self-intersection and then subtract some contribution from this base component. But again, if you know your variety well, you can write a formula for that, and you can actually integrate this and compute this expected vanishing order. And then now I can explain this value criteria. So this was proved independently by Fujita and Lee very recently in 2019. They showed that a Fano variety is K semi-stable if and only if the log discrepancy is greater or equal than the expected vanishing order for every divisor E. And so this is actually a very good criterion to prove that X is not K polystable, or it is not a Kähler-Einstein metric, because you just have to exhibit one divisor for which this inequality fails. And actually, Fujita, after proving this, Fujita went through the classification of funnel threefolds and checked in many cases those for which you could find it. So he would look and find some suspicious divisor E on the funnel and then compute this invariance for it. And then in this case, he proved that many of those funnels were not K polystable. So this is a very good criterion for showing that something is not Kähler-Einstein. And now, finally, with this is one of the criteria. There are other tools that we can use, but then now let's go back to the problem to the Calabi problem in the context of funnel threefold. And so now we are interested in using this theory to understand which three-dimensional funnel varieties admit Kähler-Einstein. And again, let me just remind you the funnel team that worked on this. So this is me and Anna Maria Kastrapet, Ivan Chelsto, Henry Fujita, Anne-Sophie Calogeros, Jesus Martinez Garcia, Konstantin Shramov, Hendrik Soos, and Nivedita Viswanathan. And so basically what we proved is that for each of the 105 information families of three-dimensional funnel varieties, we determine whether or not the general member of the family admits a Kähler-Einstein metric. And this is what we found. So for 78 of the families, the general member admits a Kähler-Einstein metric. And while for 27 of the families, no member admits a Kähler-Einstein metric. So in principle, it could be possible that the general member does not have a Kähler-Einstein metric, but then you have some special members that do. So this does not happen, at least in the three-dimensional case. We do not know whether this could happen in higher dimensions, but in dimension 3, this did not happen. And let me also point out that many of these cases were already known before. So there were the 65 of the families, the answer was already known, and this was because for some special classes of Fano, we had good criteria. For instance, for products, if you have a Fano variety that is a product of Fano varieties, it will be K-column stable even if each factor is K-column stable. Also for toric Fano varieties, there is this very beautiful criterion. So for a toric Fano variety, so we know that there is this combinatorial description for toric variety. So for any Fano toric variety, you can associate a polytope. And the existence of Kähler-Einstein method of K-column stability for toric Fano is equivalent to the very center of this polytope being at the origin. So this is a very nice and very easy to check. So for instance, all the toric cases were known, and so there were some other tools that were available for some classes of varieties. So many of them, for instance, Fujita checked for all of them those that admit an exception of the no exceptions. So so all the varieties that have a divisor on X, not on some model, birational model on X, for which that inequality fails. So for this cases, so these were already known, but there were still 40 cases missing, and these are the ones that we attacked in our project. Yes.
And so for viewpoint 22 case.
So for instance, from the 105, 65 were already known. And then we worked out the 40 remaining ones.
But viewpoint 22 general member to.
Yes, for 70. So previously known cases, so they were known, but they were in both categories. So some of them had Kähler-Einstein and others no. And this is and those numbers there are for all of them. For the 105, this is the statistics that we get.
Right. But I mean, you can.
Okay, so let me explain to you some of the tools that we apply when we run this project. So the first tool is the Fujita-Lee evaluative criterion. So let me just remind you that Fano variety is K. It will be K semi-stable if and only if we have this inequalities between the log discrepancy and the expected vanishing order. For stability, we would have to have the strict equality. Also, there is another very important invariant, which is called the stability threshold. So this is the infimum, so this is the delta invariant of X. So this is the infimum for all divisors on every birational model of X of this quotient. So for instance, if you want to prove that X is semi-stable, you would want to prove that this infimum is greater or equal than 1. And now, but also this stability threshold, so this has to be greater or equal than 1, say for it to be K semi-stable, but it can also be interpreted in there are characterizations of this invariant, using other tools. So I don't want to go too much into details, but this can be also interpreted as a limit of log canonical thresholds on certain anti-canonical divisors. So this is uses a lot the work of Birker, but then this allows us to give us a different interpretation of this invariant. And then there are tools for estimating this invariant. So there is in particular, there is what is known as the Aubin-Zwan theory of admissible flags that is very, very efficient, a very efficient way of estimating or giving, say, lower bounds for the delta invariant, for the stability threshold. Well, also something that we explore a lot is the fact that there are invariant value criteria. So what do I mean by that is that if your variety X needs many symmetries, so you can look at the automorphism group of X, then instead of checking this, computing this invariance for any valuation or any divisor, it is enough to compute it for equivariant divisors, so divisors that are invariant under the group action. So this is why I said that if your variety has many symmetries, this is good because then there is actually less that you have to check, or it's easier to estimate this stability threshold. And also another very important property that we use is the fact that K stability and also K semi-stability is an open condition. So, if you prove that a certain Fano variety is K stable, then an open subset in its deformation family is going to be K stable. So if we are interested in deciding whether the general member of the family that makes a Kähler-Einstein matrix or is K stable, then it is enough to prove that one member is stable. And then using this, what we do is to explore symmetry. So if we're interested in one certain family, instead of trying to prove that a member of this family is stable, we find one with many symmetries. And then because we have this equivariant value criteria, then there is less to check, and it's easier to prove that this one model with many symmetries makes is stable. And then we use the openness of K stability to conclude that a general member in the family is stable. So as I said here, this is K semi-stability is also an open condition, but then there is a subtlety that so far we do not know that K polystability is open. So this is not known, but in any case, in many cases we can go around this and apply these tools. So this is what I wanted to tell you today. So this, as I said, the results are going to be published soon in this book. And I thank you very much for your attention.